In this lesson, we are going to learn about the inverse of the exponential function, and that is called the logarithmic function, or the log function for short. A log function, as I mentioned, is the inverse of the exponential. So when you look at these forms, log base b of y equals x, if and only if, that's not misspelled, that's if and only if, y equals b to the x power. So one way to take a look at this is by using what's called the curly law. So if you start in log form, you take the base raised to the x power equals y. And when you look at our exponential form, b to the x power equals y. So those are equivalent forms. So taking a look at an example, thinking about this with some numbers, log base 3 of 81. Because logs are new and we're used to thinking in exponential form, what you want to do to answer this is 3 to what power equals 81? And the answer is 4, because 3 to the 4th power equals 81. So the common log is a log base 10, and by the way, the common log is the only log that your calculator knows how to evaluate. I shouldn't say that. There is another log that we'll get into in a little bit, but log base 5, for example, or that one that we just looked at, log base 3 of 81, your calculator cannot do that for you. So you need to know how to work with logs in your own brain. But for the log base 10, we don't actually write the base. We just write log of x, and we know that that's base 10. A couple of properties of logs. Log base b of 1 equals 0, because, using our curly law, b to the 0 power equals 1. And another property is that log base b of b equals 1, because b to the first power equals b. All right, first we're going to practice converting between log and exponential form, although we did just see a couple of those. So the first example is we know that 3 squared equals 9. Now we're going to rewrite that in log form. Now the curly law doesn't work as well when you're going from exponential to log form, but I still think about that when I put it in log form to make sure that I have it set up correctly. So the first thing that you do when you put it into log form is the base of the exponential becomes the base of the log, and then the exponent and the answer kind of flip places. So log base 3 of 9 equals the exponent, or 2. And as I mentioned, you can always check yourself with that curly law. 3 to the second power equals 9. Going from log form to exponential form is much easier for me. I just use the curly law. 25 to the 1/2 power equals 5. Because remember that 1/2 power is the same thing as a square root. So another way to say that is the square root of 25 is 5. Now we're going to take a look at the graph of the log function compared to the graph of the exponential. So we're going to start with 4 to the x power. Sorry, this is formatted incorrectly. That should be 4 to the x power. It's formatted correctly here. So first we just pick some values for x. We need to see what happens for negative as well as positive values. And we've got 4 to the negative 2 power. Remember, a negative exponent means you flip it and move it to the denominator. So this becomes 1 over 4 squared, or 1/16. 4 to the negative 1 power is 1 over 4 to the first, or 1/4. Anything to the 0 power is 1. 4 to the first power is 4. And 4 squared equals 16. So for its inverse, the inverse would be y equals log base 4 of x. And remember, when we learned about inverses, we switch the x and the y. So when we graph them, those coordinates also switch. So all of my y values become my new x values, and my x values become my new y values. All right, so we're going to plot these two on the graph, and then we'll talk about domain and range. So my 4 to the x power, we start at negative 2 and go up 1/16. And of course my calibration is off as usual. Negative 1, 1/4. 0, 1. 1/4. And 2/16 doesn't fit on the graph. So with the exponential function, what happens is it starts very close to the x-axis. The x-axis is actually an asymptote. And it increases when the base is bigger than 1. When the base is between 0 and 1, we'll see what happens to that a little bit later. So now we're going to graph our inverse, or the log function. So again, thinking about that imaginary line at y equals x. Sorry, I'm trying very hard with this calibration to make it work. So it's the one that goes diagonally right through the middle of the graph. So think about taking that red graph and flipping it across our green line. That's what happens for our log function. So we have 1/16 -2, about there, not on the x-axis, the y-axis. 1/4 -1, 1, 0, 4, 1. And then again, the 16/2 doesn't fit on our graph. So let's see if I can get this one graphed a little bit better. So this one has the y-axis as the asymptote. And if you notice, you can't put a negative value into a log function because you don't get a negative value out of an exponential function. So look at what happened when we put negative values in for x. It turned it into a fraction, but it did not make it negative. So the domain, let me do this in red to keep these separate. So the domain for the exponential function is all real numbers. You can put negative numbers in as an exponent, you can put 0 in as an exponent, you can put positive numbers in as an exponent. However, the range, we only got values greater than 0 because that x-axis is an asymptote. You never actually get 0 as an answer. Yes, the numbers are going to get really small if you put -100 in as the exponent. 1/4 to the 100th power is extremely small, but it's not actually 0. For the inverse, what happens is the domain and the range flip. So the domain of the inverse is x is greater than 0, and the range of the inverse is all real numbers. So we can only put positive values into a log function, but we can get any values out of the log function, positive, negative, and 0. Last slide, and here is evaluating some logs using mental math, which I know you have to because your calculators won't do logs of other bases. So, part A, when we evaluate a log, remember, use the curly law. 4 to what power gives us 64? So you can think about it like this as well. 4 to the 3rd power equals 64. So log base 4 of 64 equals 3. Looking at B, 2 to what power equals 1? 2 to the 0 power equals 1. So log base 2 of 1 equals 0. Next example, it's the common log. We don't see a base, but we know that it's 10. 10 to what power equals 1,000? And that is 3. So log of 1,000 equals 3. You don't say the base with the common log, it's just assumed. 7 to what power gives us 1/49? So think about what we just did here with our graph. When did we get a fraction? We got a fraction when the exponent was negative, because that will flip the base. So, slide down for me. 7 to what power equals 1/49? Because 7 squared is 49, the -2 would flip the 49 to the denominator. And our last example here is the same concept as the one we just saw. Whether the base is a fraction or the answer is a fraction, you're still flipping it to get your answer. So 1/3 to what power equals 27. Think about, first of all, we need a negative exponent to flip it, and 3 cubed is 27. So log base 1/3 of 27 is -3. And here are a couple of U-try questions for you.